Okay. Yep. Well, you know.
Yeah. Yeah, and you will have a lot of people online as well. You usually have over 100 people online.
It takes a whole full house. Right. Right.
Yeah, I'm just waiting for people to finish. Switching? Okay, so we're waiting for people to get coffee.
I think we're set.
Yeah, we're good? Okay. Okay, well, thank you everybody here in the room and online for coming to today's colloquium, which is given by Aki Roberge from NASA Goddard. And I'm going to have to use my phone to read Aki's credentials so I don't miss anything. So Dr. Aki Roberge is the Associate Director for Technology and Strategy in the Astrophysics Division at NASA Goddard Space Flight Center. She received, I hope people can still, yeah. She receives her bachelor's in science from the MIT in physics, right? And then her PhD from Johns Hopkins. Her work focuses mostly on planet formation disks. So if you ever heard of the disk around Beta Pig, that's Aki. And also, it's true though. And she also works on the development of future space observatories to observe planets around other stars. She served as a deputy program scientist for the Nancy Roman Space Telescope at NASA headquarters. And she was also the lead study scientist of LUVOIR, which we now know this is what kind of led to HWO a little bit, together with HabEx. And then she's currently a co-lead of the technical assessment group for the Habitable Worlds Observatory. As you all know, a concept NASA study that is going to be hopefully our next flagship space telescope mission. And in 2020, she received a NASA Exceptional Achievement Medal for her work on LUVOIR. And she also was a core team member of the 2021 NASA Science Mission Directorate, Large Mission Study, and she also has served in the NASA Planetary Science Advisory Committee. So if you're not impressed by now, just wait until you listen to her talk. And, thank you, Aki, for coming.
Thank you, Mercedes. Amongst my credentials, actually, Mercedes and I were office mates as postdocs at Carnegie, too. So another distinguished credential there. Thank you all. Right, so I'm going to give you, just as Mercedes said, an overview of what we hope will be NASA's next flagship space observatory after the Roman Space Telescope. And to do that, I'm just going to touch on a flavor of what the science would be that Habitable Worlds could do, and only a taste because the topics are truly vast. And then also a summary of what we've done and what we will do to develop the mission concept. So this talk is pretty wide-ranging in terms of topics, high level but broad. So I plan to leave plenty of time for questions here. Okay, so starting at the beginning, what is it? Oh, that's much better, thank you. So in 2021, the Astro 2020 Decadal Survey recommended that NASA develop the first telescope that would specifically be designed to search for life on exoplanets, and we've dubbed that telescope the Habitable Worlds Observatory. But the tool we need to achieve that goal for Earth-like planets around Sun-like stars is a large UV optical near-infrared space observatory. And furthermore, that is also the tool that's needed to make great leaps in a really wide range of astrophysics areas. So, but I'm going to emphasize, not for the last time, that this image here you see is only a sketch of a notional architecture option for HabWorlds. We are at the very, very beginning of a process to mature this mission concept. So, okay. But it is hard to overstate the significance of the search for life goal that was laid out by Astro 2020, and I really can't say it any better than they did. But inherent in this, in their phraseology of this, if planets like Earth are rare, and if we do discover the signatures of life, is there's a subtle thing in there that we actually need, we want this observatory to be that if we don't find life, we've actually learned something. And that is sort of a motivating factor in Astro 2020's recommendation that the sample of habitable planet candidates we should be able to study should be a robust sample, because we really want that a non-detection to actually have told us something about the frequency of Earth-like planets and life in the solar neighborhood. Okay, so, but again, I'll say this a lot too, HabWorlds is not only about the search for life. Astro 2020 identified 3 key science themes. So worlds and suns in context, with the focus area of pathways to habitable planets. New messengers in new physics, with a focus on time domain and multi-messenger astrophysics. And cosmic ecosystems, with a focus on the growth and evolution of galaxies. And the Habitable Worlds Observatory was identified as key to 2 of these 3 themes. And so, despite its name, Habitable Worlds Observatory, the mission concept, it really does have 2 primary purposes in equal measure. And they're very much complementary. So I'm going to reiterate what NASA Astrophysics Director Mark Clampin has said, that the first part of the mission's name, Habitable Worlds, refers to the first purpose. The latter part, observatory, is meant to indicate that this must be a space telescope with a wide range of powerful astrophysics capabilities. On top of that, I actually believe that HabWorlds can have an important role to play in Astro 2020's other science theme as well, through observations that can shed light on the nature of dark matter. We can talk more about that later if you're interested. So, okay, now I'm just going to go into just a bit more detail on the science of HabWorlds. Being as it is effectively a super Hubble, the range of topics is enormous, and I'll only just be able to give you a taste of a few of them. Okay, so starting with the search for life, Earth is unique in the solar system in that it is the only planet with a global biosphere that is so abundant, it's strongly affecting the bulk chemistry of the planet's atmosphere. And from a practical point of view, this is probably the only kind of life that we can both detect and recognize from interstellar distances. So to search for life on the exoplanets that are most likely to be Earth-like, those around sun-like stars, at least as far as we know anyway, what is most likely to be Earth-like, we need to use direct observations of light that's coming from the planets themselves. So in essence, we want to take a picture of Carl Sagan's pale blue dot, as in this preliminary simulated image of the solar system, as observed with an advanced coronagraph instrument on HabWorlds. The coronagraph, let's see, actually I should use my pointer. The coronagraph has suppressed what would have been the incredibly blinding light of the central star right here, so that we can actually see the much fainter planets in orbit. Okay, but pictures of fuzzy dots is not, in fact, the real goal here. What we want to do is perform spectroscopy on that light that has been reflected by the planet. And that light has passed through the planet's atmosphere, twice actually, and it carries information on its composition. So this is, again, a preliminary simulated reflectance spectrum of the modern Earth as observed with HabWorlds. And the y-axis shows, let's use the mouse so people online can see. Where is it? There. The y-axis shows what I meant about needing to suppress the starlight by a very extreme amount, as the planet is about 10 billion times fainter than the star at optical wavelengths. And that key challenge drives the hardest technologies for Habitable Worlds Observatory. But this spectrum has sufficient signal-to-noise and sufficient spectral resolution to identify key atmospheric features, and that's what we need to obtain with HabWorlds to characterize the planet. And it's not just detecting the features, we need to measure the abundances of the molecules here. Okay, so what do we learn from this? All right, so first of all, the planet is getting brighter at shorter optical wavelengths. So that steep slope is caused by Rayleigh scattering, and that's literally our blue sky. And all by itself, that shows that the planet has a substantial atmosphere. Okay, next, we have these several very broad and deep absorption features. These come from water vapor. And their strength and their depth suggest that the planet, with modeling anyway, suggests that the planet has liquid water on its surface. And all life on Earth needs liquid water at some point in its life cycle. So we view this as a key indicator of habitability. And this really is the basis for the idea that planets have habitable zones, which is a range of distances from the star where an orbiting rocky planet could have the right surface temperature for liquid water. But honestly, the habitable zone, and sometimes I say it really should be called the we don't already know it's not habitable zone. So just because a planet is in the habitable zone, there is no guarantee that the planet's actually habitable when you consider that Venus, Earth, and Mars are effectively all in the sun's habitable zone. Only one of them is actually habitable by our standards. Okay, so and then this very strong absorption feature, very strong. It's where's the mouse again? Losing it, whatever. The way it's just dropping off like a rock here. That's caused by ozone. That's our ozone shield, our ozone layer, keeping us from getting, fried. And this deep, narrow dip right here comes from molecular oxygen. So both of these molecules are products of photosynthetic life, and that makes them what we call biosignatures. Okay, but so it's important to remember that the Earth has not always looked like that. So there's evidence that the planet has been inhabited for most of its history, like 4 billion years maybe. But over that time, it had radically different atmospheric composition. And the modern Earth, with its very oxygen-rich atmosphere, that only represents probably about 13% of the Earth's inhabited history. During the Proterozoic, Earth had far lower abundance of oxygen in its atmosphere. And that molecular oxygen feature, that O2 feature that was so prominent, that is so prominent in the modern Earth, right here, if you go up, it's practically non-existent in the Proterozoic Earth. But fortunately, the ozone feature that was so crazy strong in the modern Earth, in fact, too strong to get a really good abundance measurement, now is still very detectable and at a good strength that would allow you to get a good abundance measurement from this. So this lower but not zero oxygen state represents nearly half of Earth's inhabited history, it's thought. Okay. Oh yeah, I'm highlighting. There's ozone. Yep. Okay, so then we turn to the earliest phase of the inhabited Earth. Before the rise of photosynthesis, there's basically no oxygen in the atmosphere. Instead, methanogenic bacteria were producing large amounts of methane. And this methane abundance and possibly an organic haze are the Archean biosignatures. And so really, we want HabWorlds to be able to tell that the Earth was inhabited throughout its inhabited history. And this does, in fact, this drives a broader perspective on what the needed capabilities are for the observatory. But do note, at all stages, there is strong water vapor. So that making it actually a good species to look for first. Okay, again, HabWorlds is not only for habitable planets. You're going to hear me say this several times. So just beginning with the first part, still staying in the exoplanets area, hundreds of other kinds of exoplanets would be discovered during a direct imaging survey for habitable planet candidates. And this is just a natural consequence of the fact that most planets are in multi-planet systems. Now, the Earth is very faint. It's about the faintest thing we're going to be trying to look at. So most of these other planets will be much brighter, allowing high-quality follow-up direct spectra of reflected light. On top of which, spectroscopy of transiting planets will also be possible. And so between these two techniques, HabWorlds could perform characterization of exoplanets with a very wide range of sizes and temperatures. And that really opens up a huge opportunity for comparative planetology. Okay, so now I'm going to turn to the growth of galaxies. So there are many possible HabWorlds programs that would investigate different aspects of this question. So I'm just going to highlight a couple. So these movies show went by fast, a cosmological simulation of galaxy formation from the Illustris project. And on the left, the stars and dust show up in the optical for a galaxy growing in the relatively nearby universe. Then the right panel shows that this is really only a very small part of the picture. The high temperature gas spreads out to much larger distances, and it's flowing in and out of the growing galaxy. So red is the hottest gas, green is a little bit cooler. And at low to moderate redshifts, the red gas is emitting an X-rays, and the green is in the far ultraviolet. So to really understand galaxy formation at all times and distances, we need to be able to look at galaxies in detail in the relatively nearby universe and trace the flows of matter that are the drivers of galaxy growth. And HabWorlds can observe the far UV emitting gas in a range of important atoms and ions. And this science is a key driver of the short wavelength sensitivity of the observatory into the far ultraviolet. Okay, and then this example is meant to illustrate the power of HabWorld's greater spatial resolution for a wide range of investigations. So this low-mass dwarf galaxy at Z equals 2 is little more than a smudge to Hubble, and Roman Space Telescope will have the same spatial resolution as Hubble. Galaxies like these are the building blocks of massive galaxies. They may have powered reionization in the early universe. With HabWorlds, the galaxy substructure is revealed, including star-forming regions and tidal streams. And so deep field images like this can also detect ultra-low mass dwarf galaxies that are completely out of reach for Hubble and Roman. And finally, solar system. Like Hubble and JWST, HabWorlds could perform many important observations of solar system bodies exterior to Earth's orbit and possibly reach inwards to the orbit of Venus. We'll see. HabWorld's spatial resolution, it would provide near flyby quality imaging out to about out to the Jovian system. And its ultraviolet capability allows study of magnetic phenomena like aurorae. But really my favorite cases for the solar system involve monitoring objects with flexible cadence over long time scales to look for transient phenomena like this brine eruption on Ceres, which is the closest dwarf planet to the solar system. And cryovolcanic activity like this could be monitored on icy worlds throughout the solar system, which is in fact another way of investigating the parameters of habitability. Because it's possible that those in fact are habitable, maybe even inhabited worlds themselves. Okay, so that's the science. Now we're switching gears to talk a bit more about the technical aspects of HabWorlds. So first of all, this mission concept grew out of two earlier ones, LUVOIR and HabEx, and it's worth taking a look back at them to see where we're coming from, where we're starting from. All right, so a little bit about HabWorlds history. So in fact, HabWorlds history goes back further than LUVOIR and HabEx. I'll pick it up at the Astro 2010 Decadal Survey. And at that time, a large UV optical infrared concept called ATLAST was put forward for technology maturation. And at that time, though, the concept was primarily focused on astrophysics studies. A few years later, An internal study done at Goddard looked at strengthening the exoplanet focus for that mission, while headquarters funded 2 studies of probe-class exoplanet concepts, EXO-S and EXO-C. And then after that, the 2 large mission studies were started, LUVOIR and HabEx, and to a great extent, the last internal study and the exoplanet probe studies were feedstocks feeding into those studies, feeding into those 2 concept studies as well. Let's see, and then we have, those were done in preparation for the Astro 2020 Decadal Survey, along with Links and Origins, X-ray flagship, and far infrared flagship. And those fed into the Decadal Survey, which explicitly said, with their recommendation for HabWorlds, explicitly said, take the best features of LUVOIR and HabEx and give us something different and new. So let's see, so Astro 2020's key technical and programmatic recommendations or expectations for HabWorlds were that it should be an off-axis, unobscured telescope with a roughly 6-meter inner diameter, and I'll explain what that inner diameter thing means in a minute. Astro 2020 also said that HabWorlds should enter Phase A this decade. So Phase A is the formal beginning of the formulation phase for a NASA flight project. And then they expected that all going decently well, it should launch in the first half of the 2040s. Okay. All right, so these are the high-level specs for the LUVOIR mission concept. So as Mercedes mentioned, I was the NASA study scientist for this effort. First, we studied 2 different LUVOIR architectures. There was a big one with an 8-meter outer diameter, and then there was a really big one with a 15-meter outer diameter. And the outer diameter here, that's sort of like the point-to-point, tip-to-tip diameter of the inner diameter, which is actually what matters most for coronagraphs, is the diameter of the largest circle that fits completely inside the primary mirror, so leaving off the sort of like the jagged edges if you're a segmented telescope. And so LUVOIR B, while we always talked about it as an 8-meter telescope, which is, and it is for astrophysics studies, for the exoplanet direct imaging, for the coronagraphy, it's a 6.7-meter inner diameter telescope. It's not actually hugely different from what Astro 2020 recommended. The short wavelength cutoff of LUVOIR was 100 nanometers, 1,000 angstroms, deeper into the far UV than Hubble in a really critical wavelength range. And again, the observatory was deliberately designed to be serviceable and upgradable, so with modular instrument bays, standardized rails, latches, valves, etc. Okay, so now turning to HabEx, this mission concept had a 4-meter diameter monolithic primary mirror, not segmented. And since it was a monolith, the inner and outer diameters are the same because it's just a circle. The team also studied 8 other architectures that had smaller apertures and different combinations of starlight suppression technology. But in the end, the team decided that the most capable version of HabEx was the one they preferred. The total wavelength range was just a little bit smaller than LUVOIR's, but it did also reach into the far UV. It's very similar bandpass to Hubble. One key way in which HabEx differed from LUVOIR is in its starlight suppression technology. So both of the mission concepts had an internal coronagraph instrument. Let's see. Yeah, coronagraph instrument. The LUVOIR one we called Eclipse. They also both had wide field cameras and multi-object UV spectrographs. Those are primarily for astrophysics investigations. But HabEx employed a second starlight suppression technology, a free-flying star shade that was really dedicated for exoplanet spectroscopy. And that's the flower petal shaped thing up there in the cartoon. Okay, so that was the past. So this, again, very preliminary, notional architecture option for HabWorlds. We are really just at the beginning of taking the best features of LUVOIR and HabEx, adding new ideas, and working towards a more mature mission concept. But as you maybe saw, this option already incorporates some features of LUVOIR, like a segmented primary mirror. and some of HabEx, like a barrel to protect the telescope and to cut down on stray light. So not the open architecture, JWST style open architecture. We want a barrel. Then I'm not going to micrometeorite hit on JWST. So, so I did mention it. So anyway. Okay, again, here are our starting points for some very, very preliminary and high-level specs. That's about it right there for the telescope. I'm going to keep saying it until you get sick of hearing it. None of these are set in stone. However, they are guided by the science themes and recommendations of Astro 2020. So there is a coronagraph that covers the near UV to the near infrared, a wide field camera. One thing that we really want to consider doing with this wide field camera, LUVOIR tried to incorporate it in our study, is that we would like to try to do, we may want to do high precision astrometry with this instrument. This would have a couple purposes. One, it would measure the masses of exoplanets that we could not perhaps measure with ground-based radial velocity, extreme precision radial velocity, if the stars are too active. Or also, it would be really good for some very interesting dark matter studies. So if you think back to the SIM mission, the Space Interferometry mission, this capability could bring back some of that science that SIM wanted to do. And the ultraviolet multi-object spectrograph. This one is actually near and dear to my heart because I'm actually a UV astronomer by origins. We are thinking that there can be at least one more instrument bay, but for the moment, we're just leaving that as an empty TBD. Okay, and then on top of that, headquarters has laid out some high-level guidance for how we shall develop the habitable worlds concept. And each of these 6 items is actually very significant. And together, they are intended to incorporate many of the lessons that we've learned from other NASA flagship missions, not only from astrophysics ones, by the way. So I really could spend a whole hour talking about just these, but we're just going to go through this quick with a brief summary. So first of all, the mission development schedule shall be a level 1 requirement, like we were a planetary mission with a launch window dictated by physics. Next, we will build upon NASA's previous and current technology investments in segmented telescopes from JWST and coronagraphs from the Roman Space Telescope. And so I'll quote Mike Menzel, the JWST mission systems engineer. He likes to say, evolution, not revolution. Okay, next, we will leverage the next generation of heavy lift launch vehicles like the SpaceX Starship, the Blue Origin's New Glenn, or NASA's SLS. I'm not actually sure we needed to be told to do that. Both the LUVOIR and HabEx studies already sort of assumed those range of launch vehicles. We will plan and design for robotic servicing at Sun-Earth L2. Given, NASA believes that this is we believe this is actually going to be a real capability in, 15, 20 years, that this will in fact be possible. So we're really going to do it. We will have robust margins, scientific, technical, and programmatic, especially at the beginning. That's a key lesson from the SMD, Science Mission Director at Large Mission Study thing that I was involved with. And finally, another recommendation, which was also made by Astro 2020, is that we need to reduce risk by fully maturing our technologies earlier than we do for other classes of missions. For flagships, you need to move the technology readiness level 6 gates a bit earlier, at least one phase earlier. Okay, so that's where we've been and a bit about where we are. So now I'm going to move forward again to current and future. So this is part of the HabWorlds team at the last AAS meeting. And I'm going to say we are all extremely grateful for the absolutely beautiful HabWorlds banner that was there. That Grant made that happen. Thank you so much, Grant. That was fantastic. Okay, so right, GOMAP. So you may have heard about GOMAP and wondered what the heck that was. It stands for Great Observatory Maturation Program. So Flagship missions are, by their very nature, are inherently complex and challenging. They must be, to a great extent, one of a kind, first of their kind observatories. And that high level of capability means there's a high level of complexity. Over the last decade or so, many studies from a variety of sources have come to a general consensus about both the challenges and the solutions for flagship science missions. Again, this is broader than just astrophysics. But perhaps the most important of these reports was the Astro 2020 Decadal Survey report itself, which recommended that NASA try to mitigate many of these problems by co-developing the science, the mission architecture, and the technologies earlier and more thoroughly. And NASA has adopted that recommendation in the form of the Great Observatory Maturation Program. And HabWorlds is currently within this program. Okay, so we have set up 2 teams to work on maturation of the HabWorlds concept under GOMAP. So the first is the Science, Technology, and Architecture Review Team, START. This group will primarily focus on quantifying potential HabWorlds science and capabilities, drawing from the Astro 2020 report itself as their starting place. And then the second is the Technical Assessment Group. So this is the engineering-y team tasked with exploring the mission architecture and technology trade space. And both of these teams will be developing the models and codes that we will need downstream, with the goal, really, in my view, of having everything ready to make good decisions rapidly when the concept study phase is complete and HabWorlds can become a flight project. Okay, so here are the members of the START. Largely drawn from academic institutions. The co-chairs are CFA alum Courtney Dressing from UC Berkeley and John O'Mara from, he's the Keck Observatory chief scientist. And the START also has a number of ex officio members because, again, this mission is going to need a great deal of participation from many sectors and stakeholders. So to that end, there are 4 representatives from aerospace companies, Northrop, L3Harris, Lockheed Martin, and Ball Aerospace, BAE Ball Aerospace. And there are 2 representatives of NASA's Exoplanet Exploration and Cosmic Origins Program Offices. And then we have 2, 4, 6, however many we have up there. Sorry, we just added one. Representatives of the Japanese, the European, and the Canadian space agencies. The Canadian, Christian Marois, was just added like a couple of days ago. So. Okay, and here are the members of the Technical Assessment Group. Now, for legal reasons, they are drawn from NASA centers and JPL only. And the tag is being co-led, it's joint leadership from Goddard and JPL. So 2 lead engineers, Lee Feinberg and John Ziemer, and 2 scientists, Bertrand Menison and myself. Okay, but there is really a lot of work to do. It obviously needs expertise beyond what can be accommodated only within the START and the tag. So thus, we are forming working groups, and we have invited the science, engineering, and technology communities to participate. And there's been a gratifyingly huge response from the community with, I checked the other day, it's over 900 volunteers as of a couple of days ago. And, oh, drat, just a moment. Well, it shouldn't show you. That would be really insecure if it did. Okay, where was I? Right, these are the current working groups and their co-chairs. So on the left are the very science-focused groups. On the right are the very technical-focused groups, but it's really a continuum, and we have many groups that fall somewhere in between. Either they are joint or community working groups, we are calling them. Most of these also have sub-working groups, and the full list of that is available on the HabWorlds website, which I'll point you to at the end. And I'm going to say thank you very much to Mercedes for agreeing to co-chair the ground-based astronomy in the 2030s, 40s working group, because this is important. The rule of thumb is if there's a chance of doing this from the ground, you do not try to do it from space. And there's a few really key questions that I hope you can either answer or maybe get at least a consensus opinion on what will be possible with the ground-based facilities in 2030s and 40s. And actually, we'd like to have that information soon so that we don't try to kill ourselves doing something on HAB worlds that we don't have to. Okay, and because I'm NASA, I have an irresistible impulse to show an org chart filled with acronyms, and this one's for you, Gary, wherever you are. So this is the leadership team for the HAB Worlds maturation efforts under GOMAP. The headquarters members are Julie Crook, Megan Anstel, and Josh Pepper, the program executive, program scientist, and deputy program scientist, respectively. Megan is actually from the solar system division at headquarters, which is actually very nice. You add in the START co-chairs and the TAG leads, and that gives you the GOMAP integration group, the GIG. Okay, then we have the START and the TAG members who are responsible for forming and guiding and participating in the working groups and sub-working groups. And then finally, there are the long-standing NASA program analysis groups. So we hope to benefit from their community volunteer efforts, and we look forward to trying to coordinate with them. Okay, so what are all these people going to be doing exactly? All right, here's a high-level summary. So we spent most of 2023 planning activities and setting up structures and teams. At the January 24, the last January AAS, we were ready to invite the community to participate in the working groups, which are forming up now. So now the work begins. Over the next year or so, the groups will look into the potential science, develop codes and models, assess technology gaps and technology maturation roadmaps, and explore the architecture trade space. And that work, we intend, shall bring the Habitable Worlds Observatory to what's called concept maturity level 3, which means at that point you have explored the trade space. So ta-da, right, that looks super easy. Right. Here's a little more detail on what the work actually is. So from the science side, and for the science and the joint working groups, their first step really is to articulate what the possible science goals for HAB worlds might be based on Astro 2020. I must emphasize again, we are not setting science requirements for HAB worlds anytime soon. That is the job of a future flight project in phase A. Possible goals are high-level expressions suitable for saying to your neighbor or your cousin or your congressperson. So I'll illustrate what I mean. I use this solar system example. It's sort of neutral. How did the seeds of solar system planets first come together? Okay, then they need to define the investigations needed to address the goals. And there could be many ways of doing this. And they need to decide which ones are ones to pursue for now. So in this example, the objective is discover trans-Neptunian objects down to sizes that distinguish between different planetesimal formation scenarios. Okay, then they need to determine what's actually going to be measured, what types of targets, how many, and most importantly, why. And now the first numbers come in. So now we've got detection of 30 TNOs with diameters of 4 kilometers out to 40 AU to constrain the small end of the size distribution at X precision. I don't know what X is supposed to be. That's why I have X there, what you get with 30. And then once that's done, you define the needed observations to get those measurements. So here it would be detection of, better than, brighter than 31.5 magnitude objects, signal noise 5, in a 0.017 square degree region imaged in R-band. So you get specific like that. So those of you who have worked on mission concept development before will recognize that this work feeds the first 4 columns of a science traceability matrix. That's great. But what we really want to do is quantify the science returns as functions of observatory capabilities, not just a few point designs of a handful of observing programs. This is critical because we really need to understand the breakpoints where the science returns do not very smoothly with changing observatory parameters. The places where it doesn't just degrade, but it falls off a cliff, those are the things we really want to know now, really early. On top of which, all of these parameters, astrophysical, observational, technological, these parameters are actually all correlated with each other. And we want to really do a better job of taking that into account so that we can truly find an optimal space in this very complex problem that we have. So, to that end, we are going to follow the lead of our engineering colleagues and build an integrated science model that will eventually connect to the integrated engineering model. They've been doing that for some time now. But as far as I'm aware, this hasn't been done before for a flagship mission concept, and only maybe very recently for smaller mission concepts. For the moment, we're calling this code framework DISRA, Dynamic Integrated Science Return Analysis, and I have been dreaming of this thing since LUVOIR days. Okay, so on the technical side, the working groups will be developing what we are calling exploratory analytic cases. Again, I apologize for all these acronyms, many of which we've just invented. So these are basically notional mission architecture options that will be used to explore the trade space. So our goals for the EACs are to practice our end-to-end modeling, identify key technology gaps, and interestingly, provide feedback to rocket vendors as soon as possible on our future needs to help maybe influence the direction that they develop the fairings in particular, the launch fairings. Again, I cannot say it too strongly. We do not expect any of these EACs to become a baseline design for HabWorlds going forward. So compare this sketch. Over on the left, that's early JWST. That's final JWST. We are over on the left right now. Okay. That being said, here are sketches of the round 1 EACs. The first two are off-axis designs with 6-meter inner diameters. The third is an on-axis design, so the secondary is in front of the primary and there's an obscuration. And that one's a little bigger to make up for that central obscuration. So we plan to explore these architectures for about 1 year, build up our integrated modeling infrastructure, and then fold what we learn into a second round of EACs in hopefully about a year. Okay, so you can find out more about what's going on the NASA HabWorlds website, and in particular, there's instructions to sign up for our email distribution list there. Also, we are still soliciting volunteers for the working groups, and 1,000th volunteer gets a free toaster. I think I'm actually going to do that, I think. And then again, the best place to interact with the HabWorlds community is on our Slack workspace, and that's the join link right there, the HWO community Slack workspace. Okay, good. There's plenty of time for questions. Good, that's what I hoped for. So I'm just going to end with reminding folks that Astro 2020 envisioned HabWorlds as the first of a new generation of multi-wavelength great observatories. And our efforts to mature HabWorlds in a new and improved way are going to feed into the development of possible future flagships. And we are forming a GOMAP synergies working group that's intended to capture right now what we're doing right and what we do wrong with an eye to that future. Although if they see us doing something wrong, I hope they won't keep it to themselves. But I really hope that we can make Astro 2020's vision a reality and create a new golden age of multi-wavelength astronomy. But again, doing this is going to take effort, dedication, and a significant amount of time. So, right, thanks. And there's plenty of time for questions. Good. Okay.
Thank you, Aki.
Yeah.
Right on time.
Yes.
Okay, yes. So questions in the audience?
In here. Yeah. Doesn't sound like it. Nope. They won't hear you online, I think, if we don't use the mic, so. Here, let's do this. Okay, here you go.
Yeah, so my question is whether it's been decided to what extent the Habitable Worlds observations will be more survey-driven, like Roman, or more PI-driven, like WST?
That's an excellent question. So when I talked about that wide field camera, that's not wide field by Roman standards. It's more wide field like by Hubble standards. So a few, maybe a few arc minutes by a few arc minutes. So as it was envisioned, this is really more of an observatory more in the Hubble and JWST mode as a pointed observatory rather than a survey one. It's not that wide field, not by Roman standards, which is just unprecedented, by the way, in how big of a field of view that telescope has. So that would be my guess on that one. Okay. I'm gonna do here. I'll walk around.
Thank you. I have two entirely different questions. The first, technical. The goal of light suppression to a level of 10 to the 10 is ambitious but necessary. My recollection is that to achieve these very high contrast ratios, the delta lambda over which you can operate. You showed spectra going from 1,000 angstroms out to 1.8 microns. What is the thinking as to how you would combine the high contrast ratio with the relatively broad wavelength coverage? And after you answer that, I'll ask my second, easier question.
Yeah, got it. Yeah, that. Sorry. What the exoplanet spectrum that I showed doesn't go to 1,000 angstroms. It went to it's more like 200 nanometers. That being said, that is true. That spectrum implied that you're getting that all in one shot. You're not. You're getting it in chunks, maybe 20% bandpass chunks, and you have to step through to get all of that.
A single coronagraph that you change masks.
Yes, you change masks, you change the deformable mirrors, you change everything, and you step through it to get all the pieces in chunks. Of course, the bigger the bandpass you can do at one time, the more efficient it is. So obviously, they're pushing the technology to try and broaden the instantaneous bandpass of the chronograph. But having to step through a wide wavelength range to get your whole spectrum, we do this all the time. This is not, this is how we use STIS, right? So.
Yeah, I didn't mean to imply that
Yeah.
it's impossible.
Yeah.
I just wondered what the thinking
Yeah,
was.
no, I should maybe put some marks on that to make it clear that you don't get that all in one shot. You have to do it piece by piece by piece.
Actually, does the 6 meters give you an inner working angle that lets you study M stars and K stars in the habitable zone? And the last question is, you mentioned all the guidance headquarters has given you. Have they given you a cost target?
All right, so K stars are great, actually. They're actually quite nice. They might in fact, early K stars, late Gs are actually maybe the sweet spot. So yes, on the K stars. M stars, there's a few of the nearest that, at least from the LUVOIR estimates, we could double, a handful, maybe a double handful of M dwarfs that we can reach the habitable zone. But they're not the prime focus. Frankly, I think my expectation would be that those would be good targets for the future ground-based ELTs to study, given as they have, they're sort of complementary. From space, you can get better contrast, in theory, bigger inner working angles. From the ground, you should be able to get worse contrast, but smaller inner working angles, and that sort of makes it complementary. So sun-like stars from space, M dwarfs from the ground would be my expectation. Cost target, no, NASA hasn't given us a cost target. The Decadal did, but that wasn't NASA. In fact, it would be unwise to do that so early. Another one of the key recommendations from the SMD Large Mission Study is don't try to price it before you know what you're building. So yeah, okay. Well,
Just talk loud.
Question is just.
Well,
I'm worried about
The people online won't be able
Yes,
to
they can
hear.
hear it.
Oh, they can hear it.
There
Oh,
are
great.
room microphones.
Oh, fantastic. Great. Then I don't need to be doing this. Great. Just yell. Okay.
I'm guessing that they have thrown away the idea of the star shade, or have they not? And if they have, are there any missions in the foreseeable future that would try and develop that technological idea?
I guess I would say that I think throwing away the notion of star shade, I think that's maybe a little overstatement. We are not starting there. However, it's potentially a very interesting second generation starlight suppression system, especially if you focused it, this is my opinion, especially if you focused it on the near UV portion, because that's very challenging. I mean, the chronograph's already hard, but the near UV channel, that 200 nanometer channel, that's even harder. So on the other hand, that might in fact end up being a sweet spot for star shades. It hasn't really been studied enough yet, I would say, though. Was there a second part of the question? Missions? No, I don't think, yeah, yes, I don't think so. Yes, yes.
How can laboratory astrophysicists help, and if they did want to join any of these groups, which group would
Oh, well, laboratory astrophysics, yes. Well, all of the, where's the working groups? I'll point them out. All the ones that need to do exoplanet atmosphere modeling could use some help from, where's my damn mouse? How do I get it back? All right, no, I was gonna, all right, why can't I find my mouse? All right, forget it. So the Living Worlds working groups and the Solar Systems in Context working groups, all the ones that are going to need to be doing modeling of generating planet atmosphere models and trying spectral retrievals on simulated data sets. I'm entirely confident that all of those people have laboratory astrophysics needs and desires. And in fact, I believe that's been written down in a report. David, did Jonathan Fortney ever finish his report on the laboratory astrophysics needs for, yes. Yes, that's published. Okay.
That's the white paper.
The white paper, yeah.
Yeah, but that's from 2017, so I don't know how much.
I don't know that much has changed since then. Yeah.
There's
Yeah.
a white paper, if I recall well, led by Jonathan Forney. And also,
Yeah.
right now, NASA Voices has an open call for science docs and technology
Yes.
docs. So that's a way to link.
Yes,
to
that's true.
astronomy.
Yeah. I'm pretty sure that Fortney's white paper is still valid. That's still probably the needs. I don't think it's radically improved since he wrote that paper. So I guess I would start there, certainly. And there is a precursor science call, NASA ROSE's call for precursor science investigations for in aid of the Habitable Worlds Observatory and actually the other X-ray and far-infrared flagships as well. So that is potentially a place that that one could propose something that was actually needed for Hab Worlds and actually maybe get it done, actually get some support to get it done. So I think John Zuhon has somewhere up there. Yes, he has one of these. He has a successful one of these precursor science proposals, so maybe he can tell you something about, developing a proposal for it. So there'll be another call very soon, actually, so.
I think it's very cool.
Yeah, okay.
All right, so, go ahead.
Can you say something more about what the major technical developments are that you needed and how close you are to the revolution versus evolution?
Yes. That high contrast goal, of 10 to the 10 roughly, drives, the really key challenges for Hab Worlds. And what we need to achieve that, not only do we need a coronagraph that is capable of doing that. Actually, you can design a coronagraph right now that should give you 10 to the minus 10 or 10 to the minus 11 even contrast. The problem is you need an equally good telescope to be paired with that coronagraph. Stability, stability, stability. We need the wavefront coming from the telescope to be what the coronagraph design model anticipated. So we need the wavefront, the rule of thumb is roughly the wavefront should be stable at the 10 picometer level over 10 minutes. So that means we need to control the temperature of this thing. We need to control or suppress every mechanical or thermal, every mechanical vibration, every thermal disturbance. Yeah, so that's hard. We also should be working on coronagraphs that are a little more robust to wavefront error, and that's actually another, that's coming along as well too. Where are we? Well, that's a good question. We actually, at Goddard, there's Lee Feinberg and Babak Saif in their lab there. They've actually demonstrated the ability to measure actual single picometer motions of components, of small scale components and mirrors and stuff, and actually to control the temperature of the mirror substrate at the sub-Kelvin level. So that's promising, but it's component level. We need to start expanding this and getting it more to the system level. Where are we right now? I'm not sure. I'd have to ask. I think I would want Lee Feinberg to speak on that one. So, on top of that, there are Ball Aerospace and Lockheed Martin are working on different aspects of the whole stability problem. So it's really going to be sort of like it's not one technology that's going to solve it. It's going to be sort of like a belt and suspenders sort of approach with many different aspects coming together. That's what I have to say about that.
Okay. Any more questions, either down here or the people hiding on the stairs?
Okay.
More questions?
Okay.
Well, so,
Oh, online?
are we going
Do-
to
I don't know.
talk about the questions or not? We actually don't have all the blocks system on this video.
Okay.
Okay, so thank you, everybody. Actually, I should have looked at this one. So, anyway, if somebody has a question on Zoom, please email it to me. No? No questions?
Okay, good.
Okay. So, once again, thank you, Aki, for a very nice talk. And we will be at the lobby if somebody wants to talk with Aki a little bit more until 3 for tea and coffee. So, thank you, Aki.
Thank you, Mercedes. So that goes there.
So like on axis of axis. I can ask more.
Nice talk, Aki. I did email Gordon Stacy with your suggestion, so we'll all await the response from there.
I'm on it. I have my phone number.
Okay, and if there's anything I can
Just wanted to make
do with
sure
regard to
somebody
this,
was on it.
you know where to find me.
Okay, thanks so much.
Yes, thank you, Gary.
Great job, friend.
Yeah.